I think I have started the gantry cutter chapter. So we'll just briefly focus about the remaining part. One complete problem I have solved in case of your parallel section. So you can see their note for further details. The basic methodology I'll discuss. Let me present my entire screen and start the recording. So we are covering this gantry girder, the moment check we are covering. As I have told you that MUX by MDX plus MUY by MDY should be less than equal to 1 for safety, because gantry girder is a beam which is subjected to biaxial bending. Already I have discussed that this is factored moments that we have already obtained. Now my task is to obtain this MDX and MDY. Now how can I obtain the values of MDX and MDY? MDY is relatively simpler. MDI is the moment capacity. This is the gantry girder section, and this is the YY axis. For MDY, we'll be considering the top part only. This I have explained on already. So MDY of this top part only about Y axis, that is given by minimum of ZP Y Fy by gamma m0 or ZEY 1.2 times Fy by gamma m0. Now ZPY you may not get from the code directly. So if you don't get, you assume ZPY equal to 1.6 times ZDY. If it is provided, okay, in your case I have calculated it, so it's not needed. So in your case we have calculated ZPY and ZDY, so it is not needed. So MDY in that way you can calculate, because about y-axis buckling, about y-axis moment, there is no lateral torsional buckling. There is no lateral torsional buckling for y-axis buckling. No, no LTV. Oh, let me take this color. No LTB. Now next about the MDX. For the MDX, we'll go to Annex E. that is from IS 800 2007. If I go to Annex E, the moment capacity about x-axis, considering lateral torsional buckling, is mentioned there. So we have to use this equation, this E 1.2. We have to use this equation, M critical of E 1.2. Detailed evaluation of this I have already done in your parallel section. So if you just see this, it will be over. So at first we calculate E M critical using E 1.2. E 1.2. You first calculate M critical. Thereafter, you calculate lambda LT, which is as per clause yeah, here it is. Lambda LT is 1. Beta B ZP Fy by M critical. So that is minimum of ZP Fy by M critical, or similar to your compression member ZP Fy by M critical, or 1.2 Zy, or 1.2 Zy Fy by M critical. So once lambda LT is calculated, we calculate chi LT, the reduction factor, and phi LT. And after after lambda LT is calculated, we calculate phi LT, and thereafter chi LT. In the imperfection alpha LT will be 0.21, as it is basically the roll section. So thereafter the FBD is governed by this equation, FBD equal to chi LT Fy by gamma m0, the buckling strength. Then your design strength MDX equal to beta B is 1 for plastic section into ZPZ into FBD. Okay, so the process will be, after lambda LT, you calculate phi LT, then you calculate chi LT, then you calculate FBD, and finally MD equal to MDX equal to, let me take a new, then MD equal to MD x equal to minimum of ZPZ FBD, or 1.2 ZDZ Fy by gamma m0. So now we know MDX, MDY, MUX, MUY, and we can check whether the combined ratio is less than 1 or not. If it is okay, then fine. If unsafe, apply a cover plate at bottom flange. This is the standard procedure what we adopt to make the gantry girder safe from moment capacity or deflection. So this is your gantry girder section. You just add a cover plate at the bottom. Again, the procedure is mentioned in your parallel class A class sections note. So that is all about the moment capacity. Now going through the next part, that is the shear capacity. We go for already maximum shear forces are calculated. Now vertical shear force is this much and horizontal shear force is this much we have calculated, and the vertical shear is resisted by the wave part only. So shear area multiplied by Fy yield stress by √3 gamma m0, that is 945 kilonewton in my case, which is more than the design shear. Similarly, the horizontal shear due to lateral thrust will be taken up by the flange portion only, the channel section and the flange of I section. So the area is effective in shear is shown in hatchet line here. So that area multiplied by Fy √3 gamma m0, it is also safe. Then the next part is the weld design between flange of I section and wave of channel section. You see, this is the wave of the channel section and this is the flange of the I section. We join the channel section and I section to the welding. At these points, we adopt the welding. We generally adopt intermediate welding to join the gantry girder section and to join the I section and channel section. So at this interface, what we do, we first calculate the shear force per unit length of girder in the longitudinal direction. Along the length, the shear force acting per meter length is given by V cube by I. So V is the factored shear force, Q is the area, is the moment from the CG of the channel section. So because this channel section is trying to slide over the I section, this interfacial shear force is acting in that fashion that I section is a separate entity, channel section is separate entity. The channel section is trying to slide over the I section whenever it is going to bend in a combined fashion, and thus at the interface there is a slip. If by welding you resist this slip, then the shear force will be acting. So what is the shear force at this interface that I have to calculate? So that is nothing but the area above this interface. Area above this interface is the area of the channel section multiplied by distance from centroid of the channel to the neutral axis of the section. So that is this distance, overall depth minus the CYY of the not overall depth, the depth of neutral axis y bar minus CYY. Thereafter, so we get the shear force amount. Now from clause 10.5.2.3, we find that minimum size of fillet weld should be 3 mm. Then no, minimum size of the fillet weld is 4 mm, because if I apply 3 mm weld, then the throat thickness is becoming less than 3 mm. So I have to apply 4 mm fillet weld minimum, and then the throat thickness is 2.8 mm, which is close than the minimum, close to the minimum, that is 3 mm. So strength of weld per mm is 0.74 into 0.7s Fu by √3 gamma m0 gamma mw, assuming side fillet, the factor 1.5 is applied. So I get that the strength of weld is 442 Newton per mm. Now, if I adopt intermediate weld, you see effective length of intermediate weld is maximum 40 mm or 4 times the size of the weld, that is 40 mm, and the clear spacing should not exceed 12 times the thickness of the thinner part or 200 mm. Thickness of the thinner part here is the thickness of wave of channel, and 200 we get 94. So if I consider this particular value, then you see the 40 mm and then 90 gap, then again 40, then 90 gap. This is the intermediate fillet weld. So 40 mm is the length of the intermediate weld and 90 mm is the clear gap. Instead of 94, I am adopting 90. And the center to center distance between two intermediate weld is 90 plus 40, that is 130. You can, since it is provided in the staggered fashion, the notation is also staggered. 40 mm is the length of weld and 130 is the center to center distance. But here still there is a check remaining, that whether in one spacing the weld strength is sufficient or not. Say after this step, after 442, after I calculate strength of the weld and what is the force coming, and the minimum size I obtain, I proceed in this fashion. Say for the intermediate weld, say for the intermediate weld, this is the staggered fashion. You see the clear spacing shall not exceed 90, and this is 40. So if I consider 40 and then 135, here also 40. So you can see that in one center to center distance, in one center to center distance, in one center to center distance, there are two such welds. So strength of intermediate weld is equal to 2. There are two such welds. The length is 40. So let me tell this as L, and the strength of this is per mm 442 Newton per mm. So that multiplied by 442. So this is the total force in Newton, which is the strength of the intermediate weld in one spacing. So this 40 is your L. That should be more than the spacing, that should be more than the shear flow, that is for the shear force coming is 396 Newton per mm. So that should be more than 396 Newton per mm multiplied by this L plus spacing. Spacing is S. L equal to 40 and S equal to 90 here. Then yeah, so it is 130, not 135, it is 130. So from that you work out what is the value of L and S. This check is often omitted in any book. So by this equation, you have to find out what would be the suitable value of L or S. You first assume a L and then work out S. So if you put L equal to 40 here, what is the value of S coming? Can you check? Can you check what is the value of S coming? Two into 40 into 440 by 396 minus 40. That is coming as 50 mm.
49.3.
Yeah, 50 mm. So that means the spacing will be L plus S. Instead of 90, it will be 50. So this will be 90 center to center. In that way, we fix actually the spacing between the two fillet welds. Okay. So this is often missed in the books. So instead of, in this case, everything will be same. instead of 130, it would be 90. So thereafter, similarly, you have to check for wave buckling, wave crippling, etc. And the most important check is check for the deflection. We check for the deflection. We check for the deflection, assuming that the with respect to center line, the crane loads are equally spaced. Equally spaced. Then the formula from the internet you will get that delta equal to WL cube by 6EI 3A by 4L in minus A cube by L cube, where A equal to L minus C by 2. C is wheelbase, so you can calculate the deflection, and we are checking that deflection is less than L by 750 as per table 6, so it is safe. Again, if it is unsafe, you have to provide a plate at the bottom, as I have shown you for the moment case, and the calculation I have narrated in your parallel class A section. So that's all about the gantry girder. Now the last part is the check for fatigue. In check for fatigue, fatigue of steel structure, steel bridges, say, or gantry girder, you see what happens for gradual repetitive loading. Or gradual repetitive loadings like this. If it is subjected to repetitive loading, like in railway bridges, you can see that the trains wheels are moving regularly over the years, over the months it is going on. So whenever the rail passes, the stress uh, stress cycle passes through that. So in that way, the variable loadings or the repeated loading is subjected to the railway bridges. Similarly, over the road bridges also, you can see over the months, days, months and years, the vehicles are moving. So it is subjected to repetitive cycles of vehicle load. So under such case, we define the stress range delta sigma. Delta sigma is the stress range, which is the difference between the maximum stress and minimum stress of a particular cycle. So in this case, you see the gantry girder is a moving load which operates over the girder over the years. So at first we are assuming that the crane operations are 200 days in a year, 8 hours per day, and on an average 3 trips per hour. And the design life of building is 50 years. Then the number of stress cycles or the load cycle becomes 3 cycles per hour, 8 hours per day multiplied by 200 days per year multiplied by 50 years. So over its entire lifespan, the gantry girder is subjected to 2,40,000 cycles of crane operations. Now, whenever the crane operates at each trip, whenever the crane operates for each trip, this is the stress diagram over time. You see, whenever the say a crane wheel is moving and it will give you the maximum stress or reaction, whatever it is, then whenever it has moved or it has stopped, then it has come to zero. So this is the starting of the operation of the crane, appearance of the maximum stress value, then again come back to the zero. In that way, for each trip, there will be one stress cycle. Here the maximum stress we can calculate, like maximum bending stress in the girder. We already know what is the maximum bending moment in the girder in the vertical plane because of the wheel load. We already calculated that what is the bending moment in the gantry girder. What is the bending? This is the factored bending moment. What is the factored bending moment over the gantry girder in vertical plane for wheel load only? This is the maximum factored bending moment in the gantry girder for wheel load only. Similarly, the shear force for wheel load only factored is this value. So then I can easily calculate the maximum bending stress by M by Z, where M is the service load. That is why it is made unfactored by dividing it with 1.5. So it is made unfactored by dividing it by 1.5. It is the service load. Z is it. So we get the stress is 137.6 MPa for bending. Similarly, the maximum stress in shear is the maximum factored shear by 1.5 to make it service load divided by shear area dTw. I get this value. This is the maximum shear stress. And minimum here you can see 0. So minimum stress is 0. So stress range, maximum stress minus minimum stress, that becomes the maximum stress itself, because minimum stress is equal to 0. Now, the next part, once I calculate the maximum stress, the next part will be obviously to calculate the strength of the gantry girder in fatigue. The gantry girder is subjected to this much of cycles of loading, and the maximum and minimum stress is this. So these are the load side. This is the load side. Now we are going to calculate the capacity side. For the capacity side, at first I have to know that what is the connection type. Detail category means the detailing, drawing and detailing. So from that, it is the detailing of the connection. So from the detail category, or what is the type of connection or member that from that governs the strength of fatigue. So we can go there. We can go there. You see, detail category. If it is a solid section, then the detail category is 118, the highest maximum detail category. Then it is bolted, the detail category is 103. Then if it has gasket edges, like here in this edge it is cut by gasket flames, then the detail category becomes 92. So higher the detail category means higher the strength in fatigue. Again, you see there is a continuous weld, so detail category is 92. So if you compare between the bolt on and weld, bolt is more stronger in fatigue. That's why railway bridges are all bolted. Railway bridges are all bolted because bolt has higher detail category than weld. It has higher strength than weld. Now continuous weld has detail category 92, whereas the intermediate weld has detail category 59. So that means continuous welds are more stronger than the intermediate weld. So in that way, the various types of detailing and their appropriate strength is mentioned here. As far from that, we obtain that, as I have told you, that since intermediate weld is used, that we have designed just, the detail category is 59. Detail category 59 means there is a parameter called FFN, that is 59 MPa. Now, how to calculate the strength? We will apply this one. We can use equations. There is a equation given there. There is a equation given there. This is the equation from which I can calculate the endurance capacity. That means if that is the number of cycle what the gantry girder is subjected to over its entire life, then what would be its endurance capacity? For example, uh, say if you are in a boxing stage and you will be subjected to say 10 or 20 blows from a boxer. Then how much punch you can endure? That is your endurance capacity. So NSC is the NSC that we have already calculated how many cycles the gantry girder is subjected to. So NSC is the number of cycles that the gantry girder is subjected to, or number of punch you are going to have. Now, what is your endurance capacity? That is your sorry. I just mistaken. This one, what number of cycle you have calculated is somewhere what I have told is okay. That can be told also. Then it depends on the force in the punch. That is your stress values. So how many number of punch you are going to have is your capital N. How many number of punch you are going to have, that is your capital N. And what is the amount of that punch, what is the thrust of each punch is the maximum stress range. So we have now two things in hand. What is the number of punch and how much impact it will provide during each punch. So obviously it depends on material to material. So if you are a very stout person, you can endure say up to 20 kicks of very high intensity. If you are a weak person, you can endure maximum 10 number of punches with medium amount. So same thing happens here. So knowing the capital N, the capacity is evaluated by this curve, which is termed as SN curve, the SN curve. Knowing the number of blow, I can calculate how much intensity of kick I can endure. So this either you can use the equation or you can use this SN curve. This is termed as the SN curve. We have one SN curve normal stress and another SN curve for shear stress. So this SN curve, S for stress range and N for number of blow. So with a particular amount of kick impact, that is the stress range, what is the force of the punch, that is the S, that is the stress range, and N is the number of punch that you can endure. So this is the SN curve for normal stress. It varies for the detail category. Connection to connection, it varies. So for 59 detail category, you see, for 59 detail categories, it is somewhere here. Yes, for 59 detail category, knowing the N, you see, 59 is the detail category from SN curve, from 59 detail category from SN curve. For NSC 0.24 into 10 to the power 6, you see NSC we have calculated 2.4 lakhs, that is 0.24 into 10 to the power 6. For NSC 0.24 into 10 to the power 6 and detail category 59, we calculate for detail category 59 and for strain 2 into 0.24 into 10 to the power 6, somewhere here, we found out what is the fatigue strength. In this case, what is the fatigue strength we calculate. So knowing the N, knowing the detail category, we calculate from the y-axis what is the fatigue strength Fa. So that we have done here. So for the NSC, we have already calculated detail category 59. We got that the maximum strength in fatigue is 170 MPa. You see that if there is no fatigue, the strength would be like if it's yield stress. Your strength will be yield stress, that is 250 by 250 MPa. But since it is subjected to fatigue based on the thrust of punch and based on the number of punch, we see that it can endure up to maximum 170 MPa when it is subjected to cyclic loading due to fatigue. So, we understand the strength of fatigue in normal stress is 170 MPa, whereas if there is no fatigue related criteria, then the strength would have been 250 MPa. So because of fatigue, it has been reduced. Like, if you are allowed to sit in the examination uh, in one times in a 3 months, you can score up to 90% mark. Now, if I ask you to sit in the examination at every 3 hours, you sit for the examination every 3 hours and prepare whatever is possible by 2 hours, then you see for this repetitive stress, you will get fatigue and you will score only 30 to 40% maximum. And after say 10-20 tests of 3 hours consecutively for 2-3 days, you will get exhausted, you will get fatigued, and you will say, okay, I am failing, I need not appear for any more test. So the same thing happens for material also. If it is dead load or live load, dead load or say constant fixed type of live load or dead load, then the structure can withstand very high amount of stress. But when it is repetitive loading, then it is quite difficult for the material to sustain. The fatigue occurs because of stretching and then contracting gradually. At each time the cycle is passing, it is stretched, then get released. Because of this stress cycle repetition, one time the material get fatigued and it fails in much lesser strength than that expected. So from figure we obtain that thereafter there is a table 25 in IS 800. There is a table 20. Once I calculate the strength of fatigue, that is 175 MPa, we have to apply some factors, because what we obtain is the uncorrected fatigue strength. Then we will be applying the partial safety factor. What are the partial safety factor? There are 4 cases. One is periodic inspection maintenance of the detail category or the connection is good, or it is our second case is it is inaccessible. In our gantry girder case, you see periodic inspection or maintenance accessibility to detail is quite poor, because gantry girder is located at 10-meter height from the ground. Who will go and regularly check whether all welds are intact or not? Because detail category 59 is for the intermediate weld. When the fatigue crack will propagate, it will propagate through the intermediate weld. So here the concern is on the fatigue safety of the intermediate weld. That's why the detail category is 59. So should I be able to check regularly all the intermediate welds whether they are in order or not? It is not possible. So that means it is not accessible. So that periodical inspection chance is very poor. So then this is our applicable row. This number 2 is our applicable row. Then there are 2 consequences of failure. One is fail safe and another is non fail safe. Fail safe means even if 2-3 intermediate welds of very high stress zone get failed or started with fatigue cracks, still your entire gantry girder will not fail, because it will then show some vibration whenever the fatigue cracks originates from the intermediate weld. The you will see there are large noises on the crane and vibration. So right from the initiation of the fatigue crack, your gantry girder is not going to fail. It will take some time to propagate the crack, and once number of intermediate welds get damaged, then it will fail. So that means whenever I'll see that there are large jerks or sounds during crane operation, we can go for checking and we can rectify the welding. We can redo the failed intermediate welds. So in that way, even after failure in fatigue, the structure overall becomes safe. That is the name of the consequence of failure is fail safe. And in our case, it is the case. So our factor of safety is 1.15. On the other hand, where the consequence may be non-fail-safe, like in bridge bearings. If I use a pot PTFE type steel bearings, and if that bearing fails, then the entire bridge will readily fail. So that pot PTFE bearing failure is a non-fail-safe type failure. Then you have to adopt a higher factor of safety. So then using the factor of safety is 1.15, I get the strength in normal stress. Actually from equation we are getting 162.3, from figure we are getting 170. In your case you can simply apply the figure, you need not go for the equation. So that 170 or 162.3 by factor of safety that we have just obtained is 141.1 is the fatigue strength. And maximum stress, you see, maximum stress coming is 137.6. So maximum stress is 137.6 and your strength is 141.1. So it is safe. Now for the shear stress, again we'll repeat the same procedure and we'll check whether it is safe or not. We are seeing that it is safe also. So that's all about fatigue. Now only one thing is remaining. Uh, uh, Now only one thing is remaining, that is the last chapter. Check for the gantry data chapter is finished. Before going to the next chapter, if you have any question you can ask. Do you have any question? You can ask then.
Sir, while
Yes.
calculating for ZPX, you told to
Hmm.
multiply it by 1.6, but it should be multiplied by the safe factor.
Which one?
And suppose that, sir, ZDX is given and ZPX is not given, so it should be in order to get ZPX, we should multiply it by means safe factor, but you told to multiply it by
Yeah. Yes.
1.6.
Yes. Yes. Yes.
Sir, but safe
If
factor
it
is
is
not always
not,
1.6.
yeah, yeah. It is not always 1.6, but in gantry girder y-axis, you will see it is more or less close to 1.6.
Yes, sir.
Uh, you see, for this gantry girder type of section, for this gantry girder type of section, about y-axis, the safe factor is generally close to 1.6. So if you do the, if you see, what I wanted to mention is that you see later on I have deleted it because I do not require to obtain ZPY by multiplying something. Why? Because I am calculating ZPI of this flange part only, right? And that calculation I have already done. You see in your previous classes, if you see the plastic section modulus of this calculation, ZPI I can calculate manually. Plastic section modulus or the compression flange about y axis, that I can calculate manually. So there is no need of multiplying such things. Is it okay?
Yes, sir. And sir, in generally also means it is adopted that we should multiply it by 1.6.
No, that is that what when we do it, like for channel section. In channel section, when it is used for purlin, we have seen that the shape factor about y-axis for channel section is always 1.6. So then we can do it. But for this section, it is closer to 1.6, but I cannot say it will be right 1.6. So that's why that multiplication by 1.6 is okay for channel section, but it's not okay for this type of section. It will give you closer result, but not accurate one. For purlin channel section, you can multiply it with 1.6. ZPY equal to 1.6 into ZEY for channel section purlin only. Okay.
Yes.
Now the last part that I want to discuss is this one. Beam under high shear. The Gantigata chapter is over. The next part is beam under high shear. Like in cantilever beam, you see that the maximum bending moment and maximum shear force are occurring at the same section. For cantilever beams, the maximum or cantilever column, maximum bending moment and shear force are acting at the same section. So in those cases, there is a chance that moment capacity get reduced because of the presence of high shear force. Like, if you are given a very high task of doing some assignment, and at the same time, if I ask you to go for a playing cricket tournament, either your assignment will be compromised or your cricket tournament will be compromised. So in that way, if it is already in high shear, then your moment capacity may be reduced. This is not the case with gantry girder or simply supported beam, because in gantry girder or simply supported beam, maximum moments occur at the midspan and maximum shear force occur at the support. So occurrence of bending moment and shear force maximum values are different sections at different sections. That is why those sections are not under high shear. So only at the support section of the cantilever beam or support section, interior support section of continuous beam, interior support section of continuous beam, or support section of cantilever beam, where at the same section high shear as well as moment is coming, we have to check for this. So this one is beam with high shear when the factored shear force is more than 60% of its shear capacity, then we call that the beam is under high shear state, and we then calculate the reduced moment capacity by this equation. MD minus some this is the deduction because of the high shear, or the 1.2 ZEFY by gamma m0, whichever is minimum, where beta is a factor which considered this high shear aspect. MFD is the plastic design strength excluding shear area. So then the problem is check whether ISLB 350, thickness of flange, wave, etc. is given, is adequate to bear moment of this and simultaneously shear of this. Assume section to be plastic. You note that it is the high shear or low shear, it is not on the beam. Beam cannot be under high shear or low shear. It is on the section, whether section is under high shear or low shear. So first of all, we will calculate the capacity in shear Fy HTW root 3 gamma m0 as we have done. So it is safe in shear. Then we check the force, shear force is 300 kilonewton, which is more than the 60% of the capacity. That means the beam is in high shear. So I have to now calculate the reduced moment capacity. First of all, we calculate MFD, the design strength of the flange only. Design strength of the flange only is the plastic section modulus of flange only into Fy by gamma m0. Plastic section modulus of flange is equal to overall plastic section of modulus of the section minus uh, plastic section modulus of the wave. So overall plastic section modulus is given in the problem, and for wave part, what is the plastic section modulus? For wave part, this is the rectangle, this is the rectangle, and this is your x6. If this is TW and if this is D, the plastic section modulus of this wave is equal to D BH cube by 12. So sorry, BH square by 4, BD square by 4. So TW D square by 4. ZP of a rectangular section, ZP of a rectangular section of width B and depth D is equal to BD square by 4. So same thing is done here. BD square by 4, thickness of wave into depth square by 4. So total ZP minus ZP of wave will give you the ZP of flange. Then moment capacity of the flange is ZP of flange multiplied by Fy by gamma in 0 is 141.93. Then the moment capacity overall is this ZP overall Fy by gamma in 0. It's quite simple. Then the value beta reduction factor is 2V by Vd. V is the factored shear force and Vd is the capacity, that is 0.585. So MdV using that equation is uh, gross moment capacity minus reduction factor minus gross moment capacity minus flange moment capacity. So this is basically the moment capacity of the wave. So it is the gross moment capacity minus some part of moment capacity of the wave get reduced of the because of the high shear, because shear is taken up by the wave and moment is taken up by the flange. Shear is taken up by the wave. So if because of high shear the moment capacity get reduced, it is because of the wave only. So this one is the moment capacity of wave only. 193.43 is the moment capacity of the overall section. 141.93 is the moment capacity of the flange. So this minus this overall minus flange will give you the wave only. So this is the moment capacity of wave only. So then moment capacity of the wave get reduced by 58.5% because of the presence of high shear. Then this calculates to 163.3, which is more than 150, so it's okay. So that was only left. I have covered this in parallel section. Now is it okay? Is it okay?
Yes, sir.
I'll give all this material to you. Now everything I have completed syllabus. I require only 10 minutes to discuss one thing, discuss 10-15 minutes to discuss two things. Should I do it at a stretch or I'll give a 5 minutes break? I
Sir,
require only 20 minutes more.
sir, we can continue.
Okay, that will be good. Then the next thing what I want to discuss is warping and torch twisting. In lateral torsional buckling also, there is a effective length. In lateral torsional buckling also, there is a concept of effective length. But that effective length is
Thank you. सर का नंबर है। नहीं।
इसको मैसेज किए कविता में। मेल में अपना नंबर लिखते हैं।
नहीं दिखा बाहर।
कुछ नहीं।
सर डिस्कनेक्ट कर दिए थे। नहीं कर दिए। रिप्लाई आया है, इधर मैसेज किए। वेट फॉर 5 मिनट्स।
रुकता है ना जाता है। वो चलेंगे।
हाँ हाँ।
Hey, this is the breakfast. Hey, or biscuits.
सस्ता जो सस्ता रखा है वही बस बढ़िया है।
Can you hear me?
Yes, sir.
Yes, sir. Okay. My system has gone out of battery, so it's starting. By this time, let me discuss about the examination. So, in examination, there will be 8 questions, 4 questions from my part, and 4 questions from Professor Doloi's part. No separate answer script to be used. Answer all the question in the same answer script, and no codes and handbooks will be allowed in the examination hall. Okay, no codes and handbooks will be allowed in the examination hall. So whatever you will do, some formula like interaction formula of the column or the section properties of the different uh, channel section, I section, angle section, etc. will be provided. And if something
Sir,
is
how
not
many
given, 5
how
out
many
of 8.
questions we have to?
You have to answer 5 out of 8. Okay. 4 questions from my side, 4 questions from Professor Doloi's side, and altogether you have to answer 5 questions out of 8 questions. Any more query regarding that? And the question will be from the portion covered before midterm as well as portion covered after midterm. Okay. You need not think that the questions will be only after the midterm portion. The syllabus for semester will be the entire syllabus starting from the before even before the midterm and after the midterm. So from the semester start to semester end. Anything more you need to ask regarding the examination?
Sir, means will it be sub parts of questions also, or means from one question from one topic like that?
The mostly it is one mostly or mostly it is one question from one topic, because Parlin, Gantry Girder, all are you see all are standalone questions. Okay, you also you can though Parlin, Gantry Girder, these are part of seasonal class also. There will be question in semester examination also from Parlin and Gantry Girder, beam column, etc. In my portion, you know, the syllabus is Parlin, gantry girder, laterally supported beam, laterally unsupported beam, then compression member, built up column with lacing, single and loss lacing, double lacing system, battens, single channel sections, compression member. These are from the mic part. So now I think I can be able to join from the uh, so let me resume. Can you hear me? Can you hear me?
Yes, sir.
Okay. Now, the last part that we are discussing, the concept about 2 things. You know, in lateral torsional buckling of beam, we have a concept of effective length, that is LLT. And for compression member also, there is a concept of effective length, that is KL. But the definition of both these are different. You know, for fixed cage, fixed hinge case, the effective length is different for different compression members. So what the condition of the end, that is whether fixed or hinged, that is the basic criteria for deciding effective length of compression members. But for effective length of your beams for lateral torsional buckling, it is not the hinge or fixed type of criteria. It is dictated by torsional restraint and warping restraint. So torsional restraint prevents rotation above the longitudinal axis, and warping restraint prevents rotation of the flange in its plane. I'm reading this again. Torsional restraint prevents rotation about the longitudinal axis. So that means it prevents the twisting. What does it mean? So if I search in the internet, torsional restraint at in beams, and you see there are several pictures. Because of the torsion, the section try to twist. Because of the torsion, you see, because of the torsion, the section tries to twist. Now at the end, I have to arrest this twisting. How can I do that? There are several ways. You see, uh, there are two beams. If I join the flanges by this, then it cannot twist because it is get laterally supported then. So anyway, I have to support the twisting of the section. So by providing this type of restraint, or by providing this type of restraint, or by providing the cleating. You see, at the end, if I provide us cleating, then also I can restrain the uh, torsion at the end. I think it would be better if I can show you diagram. So this is, say, the end of the beam. This is the end of the beam, simply supported end. So how can I prevent the twisting of the section? So the one way may be by providing the bearing stiffener. If I provide the bearing stiffener here, you see in the both side, I am providing a bearing stiffener plate. So then this whole section cannot twist. So by providing torsional restraint, the torsional restraint can be provided by bearing stiffener. Or what we can do, I can join the end with a column. At the end, I'm joining this with a column. So by moment connection at end, then also the end cannot move, rotate. So either by providing this type of lateral support, that I have just shown, or by the way of providing bearing stiffener or providing a moment connection at the end, I can prevent the twisting. So this is the way how I provide torsional restraint. In this case, torsional restraint, we assume that it is fully restrained. Either generally we provide bearing stiffener to fully restrain the torsion at the end, fully restrain the twisting at the end. Now next is the warping. In our case, it is warping not restrained in both flange. Warping is not restrained in both the flanges. Now then I have to know that what is warping? Warping restraint prevents rotation of the flange in its plane. So what is warping? warping of flange. Let me search. Yeah, this is warping of flange. Warping means basically the distortion. Plane section remains plane before and after bending. That is our preliminary assumption. Plane section remain plane before and after bending. But if warping comes, the that uh, it gets squeezed, it get distorted. The plane section get distorted. So in that way, the plane section does not remain plane. You can see this is further example of warping. Warping means some types of squeezing. So if your flange of the beam, you see, this is another classic example of warping. You see this is the section, plane section. This is the plane section. After warping, this is the plane section. After warping of the flange, you see, it is not, the section is no more plane. The plane section is shown by this uh, this line, this box, this rectangular box was the plane section. But after warping, you see this flange has rotated in this plane, and the other flange has rotated in the reverse plane. So now the plane section is not remaining plane. It may so happen like this. You see, the plane section is not remaining plane. So that is the example of warping. So when the steel beam tries to deflect laterally, there are every chance that this type of deformation may occur. At the this type of deformation occurs. So that means flange may rotate in its plane. Flange may rotate in its plane. That is called warping. We cannot resist that. We cannot resist that. So that is why, in our case, the effective length is 1L. So KL here, for this simply supported beam also, K factor, K into L, for the effective length factor is 1. But that is not because of the ends are hinged. That is because the torsion is twisting is fully restrained at the ends, but warping throughout the beam is not restrained. That is why the factor is 1. So it should not be misunderstood with your effective length of compression members. Now, how can I provide warping restraint? So it is not quite simple to provide warping restraint throughout the length. Warping restraint can be provided by this type of attachment, which will hold the flange firmly so that it will not be able to twist. Or by provide only at the end we can provide some steel plate which will arrest the movement of the flange. So anyway, you have to arrest the movement of the flange. So it is not quite appropriate to resist the warping throughout its length. So that's why we assume that warping restraint is not there. Now the last thing that I want to discuss is about the prime force. Prime force is the additional tension force developed in a bolt as a result of flexing of connection components such as beam end plate or leg of an angle. You see, this is the situation that your this one is your column, this is your column, this one is your base plate, this is your base plate, and this is your sorry, yeah, this is your base plate and this is your column. Now say column is connected with the base plate with another plate here mentioned. So if your base plate thickness is less, say 12 mm or 16 mm, then what may happen? Because of the wind, the column get uplifted. Because of the wind, the column get uplifted. Because of the wind, the column get uplifted, and the base plate connected with the column will also flex. This is the base plate. This is the base plate. There are say 2-3 base plates. One 12 mm, another 12 mm. Many times we, instead of providing a single base plate, we provide the base plate by pieces. One base plate of 12 mm, another of 12 mm. So if this thickness of base plate is quite less, it will also flex along with the column. When column get uplifted, this base plate will also bend. You know that whenever bending will be there, the bending stress will be generated. Normal bending stresses are generated at bolt connection A and B. And you assume that this flat plate is either another base plate or the pedestal concrete. This flat plate is either another base plate or the pedestal concrete. And the base plate of that connected with the column is going up. So it is bending. Because of the bending, the extra bending force uh, Q get generated. That Q is your prime force. This Q is your prime force. So for design of these bolts, along with the tension, that is TE, in each bolt it has to resist the tensile pull of TE, plus this Q, that is the bending stress because of prime force. Prime force is the amount Q, plus this Q has to be considered for design of this bolt. So that is what is termed as prime force. So prime effect so as you have been seen here, the same picture, this type of prime may comes for connections also, not only base plate, it can be on connection beam column joints also. In beam column joints also such prying effect may be there, as you can see here, that this steel beam is connected to the column by means of angle section. When it is bending, the steel beam is coming out, so the angle section is bending, and as a result of which it is adding a prime extra force to the bolt. So it is relevant to the bolt design only. So that's all for what I intended to cover. If you have anything to say, please, or if you have anything to ask, please tell me. Otherwise, I'll close the session. Is it okay?
Yes, sir.
Okay. Then I'm closing the session for my part.
Sir,
Yes.
sir, in steel projects also, and as well as in this steel design also, means we have not considered for the thermal stresses. Why?
Yes. You see, in IS 800 2007, it is clearly mentioned about the thermal stresses. Expansion and contraction due to changes in temperature of the members and muscles shall be considered an adequate provision made be for such effect. Now, what we do? Uh, there is some figure here. What we do? We fix the maximum length for thermal expansion. Like in concrete structure, if the length of the building exceeds 45 meter, we provide one expansion joint. Because we assume that whenever there will be some thermal stresses uh, for a building which is more than 45 meter long, which is more than 45 meter long, for a RC building which is more than 45 meter long, the thermal stresses may get generated, and you have to take care of that in STAT modeling. But if your building is less than less than 45 meter in length and is made with RC, then you need not consider any thermal effect, because whatever expansion it will, uh, whatever expansion will happen, it will simply expand and no extra stress will be generated.
Open air.
Similarly, in steel structure, this is the maximum length, 90 plus 90 plus 50. So around 230 meter. So if your building length is less than 230 meter, you may not provide expansion joint. You may not consider the thermal joint stresses. You have to consider the thermal stress if the building length is more than that. But here, though it is written as 230 meter, we limit it up to 150 meter. Now, in your industrial building, you see the length of the building is less than 150 meter. That is why you have not considered the thermal stresses. We assume that, not assume, we know that whatever thermal stresses get generated, it will be, the structure will be expanded or contracted, but that will not create any stress to the structure. But in case it becomes more than 150 meter, that expansion or contraction will be significant, and that will create stress to the structure. Okay, so this is because of the length constraint. That if it is up to 150 meter, you need not consider the thermal stress, and if it is up to 45 meter in RC, you need not consider the thermal stress. After that, you have to provide the thermal stresses. Now, what we do, instead of considering the thermal stresses in the analysis, we provide an expansion joint. For RC structure, after each 45 meter, we provide an expansion joint, and for steel structure, after each 150 meter, we provide an expansion joint. But that is not the case for bridges. For bridges and culverts, they have explicitly mentioned that since the length of the bridge will obviously is generally be more than 150 meter, and for steel bridges, and for concrete bridges, it is obviously more than 45 meter. IRC code, Indian Road Congress code, tells that for bridges, you must consider the temperature effect. Okay, so everything is based on the length. You know, the temperature stress is given by that expansion is given by y alpha t. So that y alpha t, that y is the length. So the temperature, so the increase in length because of temperature is totally dependent on the its initial length. The increment of length because of the temperature expansion is totally based on the initial length. If the initial length is within 45 meter for RC structure and within 150 meter for steel structure, you need not consider the thermal effect. Okay.
Yes, sir.
Anything more?
So that's it.
Okay. Thank you then. And in the next week, if somebody wants to see mid-sem script, he can come to my chamber and see it. And
Okay.
regarding the attendance,